Hello, I am Liyang. Thank you for joining me. I'm very excited to tell you about my paper, Empirical Welfare Maximization with Constraints. In this paper, I developed new statistical rules for designing eligibility criterion for a welfare program. Here, I take eligibility criterion to be based on individuals' observable characteristics and chosen to maximize social welfare. To do this, I suppose we have access to a randomized control trial, or RCT, that randomizes individuals into program eligibility and non-eligibility. Let me give you an example for what I meant. Medicaid is a public health insurance program intended for the low-income population in the US. The eligibility criteria for young adults take the form of an income threshold. That means people whose income is below this threshold would be qualified for Medicaid. In 2014, the US government decided to provide resources for states to expand Medicaid. Suppose the state of Oregon wants to design a flexible expansion criteria where the new Medicaid income thresholds can vary by number of children people have. How should we do that? To visualize this question, I plot the income distribution by number of children shown on the horizontal axis. And the question is where to draw these three different income thresholds depending on the number of children below which people become eligible for Medicaid. The rules I developed in my paper are able to pick these thresholds based on any experiment that randomizes individuals into Medicaid eligibility and non-eligibility. It turns out Oregon has done such experiments back in 2008 as part of the Oregon Health Insurance Experiment. So we can think about ways to use this experiment to design the optimal allocation of Medicaid, and this gives a statistical rule that maps the RCT data we observe to an eligibility criterion. A recent econometric literature has proposed one such rule called Empirical Welfare Maximization, or EWM. This literature has proved convergence properties of the EWM rule in many settings, but I want to extend it to the setting where the cost of providing eligibility to a given individual is unknown. This can happen for several reasons. There can be imperfect take-up, so not everyone allocated the eligibility would eventually enroll in the program, costing nothing to the government. Or there can be heterogeneous costs such that cost projections are difficult. Ideally, we would like the statistical rule to select a feasible criterion such that the budget needed to implement this criterion would not go over a fixed threshold and satisfies a budget constraint. But we would also like to select an optimal criterion in the sense that it achieves the highest feasible level of welfare. In the setting I mentioned earlier, where the cost is unknown and needs to be estimated, realistically, there is just no way that statistical rules can always select feasible and optimal criterion no matter what data we observe. So instead, I focus on deriving rules that are asymptotically feasible and asymptotically optimal, which I will define these two properties momentarily. My contribution in this paper is therefore to investigate the theoretical implication of having to estimate the cost for whether and how we can find these rules. Now that I've explained my motivation, let me introduce the setting I focus on more formally, describe the two rules I propose, and conclude with an illustration. So by eligibility criterion, I mean an indicator function g of x, which is equal to 1 if an individual with observed characteristics x is assigned with eligibility and 0 if not. There are two other random variables of an individual relevant for determining the optimal allocation, which are benefit and cost. I use gamma to denote the benefit, which is defined to be the difference in individuals' potential outcomes due to eligibility. Gamma is unobserved because it involves potential outcomes. I use R to denote cost, which is the potential resource government will need to spend to provide eligibility to this individual. So R is also unobserved before an individual receives the eligibility. I use P to denote their joint distributions, And since we want to propose statistical rules that work for many distributions, P is taken to be unknown. When resources are scarce, policymakers naturally want to prioritize eligibility to individuals who will benefit the most. To formalize this as a constraint optimization problem, let me define the following two functions that take the criterion G as an input. Welfare function is the average outcome under criterion G. After rearranging this average, we notice that for the purpose of optimizing with respect to G, the baseline outcome drops out, and the welfare function is just the average of the product between benefit gamma and the criterion function G. The budget function is the budget needed to implement criterion G, which is the average of the product between cost R and criterion function G. Starting with a set of criteria available to policymakers, denoted with script G, the constraint optimization problem is to find criterion G that maximizes the welfare function, subject to the constraint that the budget does not exceed a fixed threshold K. The solution is, by definition, the feasible and optimal criterion, denoted with G star P. You may have noticed that I index everything with a distribution P, and that is because the welfare and budget functions depend on P, and so is the set of feasible criteria. Policymakers would like to solve the problem directly, but the challenge is both welfare and budget functions are unknown because they involve unobserved quantities, benefit, and cost. We also do not know their joint distribution P to evaluate these two functions. But we have access to an RCT that randomizes the eligibility, so we can construct their sample analog estimators using benefit and cost estimates denoted with gamma star and R star. In particular, gamma star is the inverse probability weighted estimator, and we have a similar formula for R star. If instead we only have quasi-experimental data, then we should use the doubly robust scores as the estimates. These estimates are well known because they are unbiased and asymptotically normal if we use them to estimate the average impact of the welfare program. But here we want to use these estimates to approximate two functions evaluated across many criterion functions G. It turns out that as long as the set of criterions is not too complicated, these nice properties extend to the optimization problem that the sample analog welfare and budget functions converge to normal distributions uniformly over criterion functions G and also uniformly over many distributions we want to consider. This convergence means we will have some control over the asymptotic behavior for statistical rules that use these sample analog functions as inputs. Now let me define the two desirable properties for statistical rules that we want to propose. First is asymptotic feasibility, which says as sample size increases, it is likelier for the statistical rule G hat to select a criterion that satisfies the constraint. This definition is specific to the distribution P, and we can make a uniform version that holds for many distributions. The second property is asymptotic optimality, which says as sample size increases, it is more unlikely for the statistical rule G hat to select a suboptimal criterion whose welfare is strictly less than the maximized feasible level. Now, the natural question you might have is, can we find a statistical rule that achieves both properties simultaneously for many distributions? This question leads to a theoretical result I proved in the paper, which is that if we want to allow a general class of distributions, then no statistical rule can satisfy both properties simultaneously, uniformly over all these distributions. You can think of this result as the price we pay for staying agnostic about the distribution, such that the setting with unknown cost and a budget constraint is too complicated for any arbitrary draw of the data to approximate. To get around this negative result, I instead propose two statistical rules that maximize welfare but achieve the two properties one at a time. I call them mistake controlling rule and trade-off rule. When we should use one rule or the other depends on our attitudes toward the budget constraint. That is, whether policymakers are willing to tolerate any violation to the budget constraint. Let me tell you how these two rules work. The mistake controlling rule finds the criterion G that maximizes the sample analog welfare function over a data-dependent subset of criterion. To construct this subset, we tighten the sample analog budget constraint by a negative critical value that we can calculate based on bootstrap for a pre-specified significance level alpha, say 5%. The tightening is also proportional to the estimated variance for the sample budget function, which we can calculate based on the data. Operationally, this mistake controlling rule constructs a simultaneous 1 minus alpha level confidence set for all the sample analog budget functions and excludes criteria where the upper bound of this confidence set exceeds the threshold K. This way, it is guaranteed to only select an infeasible criterion less than alpha % of the time asymptotically, and therefore achieves asymptotic feasibility for many distributions. So mistake controlling rule maximizes welfare but focuses on asymptotic feasibility. The second rule I propose, the trade-off rule, focuses on the other property, namely asymptotic optimality. It selects the criterion that solves a max-min problem, where the objective function has the sample analog welfare function as before, but penalizes for the amount the criterion exceeds the sample constraint. How much we penalize is determined by the trade-off coefficient lambda bar, which bounds the marginal benefit from violating the constraint. Effectively, the trade-off rule is able to relax the budget constraint and therefore is asymptotically optimal for many distributions. Now I turn to the Oregon health insurance experiment I mentioned earlier and applied both rules I proposed to this dataset to select Medicaid expansion criteria. Both rules pick eligibility criteria that prioritize Medicaid to individuals with children. However, on the left, you see the mistake controlling rule is constructed to limit eligibility to satisfy the budget constraint with high probability. So if policymakers are financially conservative and do not want to violate the budget constraint, mistake controlling rule is more appropriate. On the right-hand side, you see that if policymakers are willing to tolerate trade-off, then the trade-off rule is more appropriate because it's constructed to pick a more generous criterion to trade off any additional welfare gain for cost overrun. Now, let me conclude. As you have seen, my paper contributes to the EWM literature by considering real-world budget constraints where the cost is unknown and needs to be estimated. I propose two new statistical rules, mistake controlling rule and trade-off rule. These two rules can be easily implemented following an RCT, but the framework I developed is general and can be extended to other constraint optimization problems, where whether a criterion satisfies the constraint needs to be estimated. Thank you again for listening to my presentation, and I'm happy to answer any question you have.